Hi everyone. So today I'm talking to Dave Bell from MIPS, and we're going to be looking at the potential use cases encompassed within physical AI. Hi Dave, how are you?
I'm doing well. How are you?
Great stuff. Okay, to start off with, maybe you could explain the four key pillars that MIPS has identified as being the foundation for physical AI.
Yes, MIPS is bringing differentiated compute solutions targeting a new era, that of physical AI, where equipment is leaving the screen and the data center and coming into the physical world around us. And as part of that environment, it's important for the equipment to be able to sense, think, act, and communicate to be able to operate amongst people and amongst objects in the physical world. In particular, sensing involves being able to take input from the physical environment, be it speech, sound, vibrations, temperature, any of the physical attributes that you might interact with in the day-to-day real world. The thinking portion is obviously interpreting that data to do something with it. The action is the action that then takes place, whether that's movement or some kind of alternate operation. And then communication is really a piece that ties all of that together, whether that's communication within a physical chip, within the larger equipment, or even a distributed type of larger system. So MIPS is focused in each one of these areas in each of our product developments.
Okay, so it's coming back to the sense part. Obviously, that could be, as you said, there's a number of different things it could be, and I guess it could also be a multimodal combination of multiple different things, especially when we talk about, autonomous vehicles and stuff like that, or AMRs. They're going to be picking up LiDAR signals, imaging signals, and everything like that. So that's one aspect of it, that you've got to have the ability to deal with different sources. And I guess those have all got to be synchronized together as well. Is that quite an important part?
That's absolutely right. So if you think of autonomous vehicles or even driver assist equipments within a vehicle, you can look at sensing in terms of interpreting vision data, radar data, different modalities like LiDAR and ultrasonic sensors. Really, you have multiple inputs that are sensing the environment around the vehicle, both at distance and near to the vehicle. And so it's important for the overall sensing subsystem to be able to take inputs from these different modalities and a multitude of sensors and make sense of it all, to play on the word, and process multiple streams of input in order to take intelligent action afterwards.
Okay. So, and then in terms of, obviously, sort of these things are going to be mainly at the edge. They're going to be sort of dealing with basically rapid responsiveness. So I suppose obviously the keeping the latency levels as low as possible, being able to react quickly is going to be really important then as well. Yeah.
That's an excellent point. So beyond just the compute, the scale of the compute itself in terms of actually processing the input data, latency is a very key attribute. So again, if you think of a vehicle and it's detecting an object that is in the vehicle's path, traveling at a high rate of speed, being able to react in a very short period of time is essential. So it is important to be able to both compute things effectively in a short period of time, but also to communicate the response to the next phase of processing in a short period. So latency has multiple steps, both the input signal itself, the processing time, and the communication piece downstream in the processing chain.
Okay, great. So in terms of the sense aspect, what would be the other key computational challenges that you need to address? So, on top of the multimodal side and the fast responsiveness and so forth, what other things are your customers likely to need?
Absolutely. So the complexity of the compute subsystem in the sense environment is varied. So it's not just about the ability for a CPU to process data quickly. Typically in these systems, you have actually a heterogeneous type of system where you have the sensor input, you have some custom logic or vision data path or radar data path that's doing specialized computation alongside the general compute. So it's important for CPU to be able to handle multiple threads of execution, multiple tasks that it needs to manage, be it the communication stack, be it interacting with physical hardware for the input, managing the file system, and actions downstream. So having a compute subsystem that is capable of multiple things operating efficiently and concurrently is very important. One aspect of physical AI is that you're not necessarily plugged into a CPU or part of a data center. You are potentially tethered, but you're often operating at the edge or even standalone, where power is a critical aspect. So doing all of the processing and managing multiple functions concurrently at low power is very important. So that's where a lot of the functionality that we have in our compute solutions comes into play.
Because as you say, a lot of this stuff is going to be in constrained environments that you've got limited, sort of energy resources and so forth. But likewise, I guess that there's got to be, some of these applications are going to be space constrained as well. They're going to have to deal with possibly quite challenging edge-based sort of working environments as well. Is that something that needs to be taken into consideration?
Correct. Area and power constraints are pretty key in the types of equipment that our products are well suited for. So the physical constraint could be both a form factor, meaning it needs to be a very small chip, and our portion within the chip even smaller. Often that comes with a premium on power, meaning we need to operate at very low levels of energy dissipation to make sure that the thermal environment's not violated. So having a small physical area, having a low power footprint is very important for the processing challenges that we're solving.
Okay, so that's cool. So maybe we could just look at illustrating a couple of potential use cases here. So, one that obviously springs to mind is autonomous vehicles, and obviously that's an area you're, sort of getting heavily involved in at the moment. So maybe we could look at the specific nuances of that.
Okay. Yeah, in automotive, there's actually several types of things that we need to be mindful of. One, like we talked about, is the power and area footprint that we're occupying, and the need to be able to handle multiple threads of execution concurrently at the same time. Another is functional safety. So in the automotive space, as well as in broader industries like industrial and robotics, there is a need to be a functionally safe end equipment. A lot of this is done at the final product level, but it does come down to both the SoC and even the IP level to make sure that we're doing things in a way that conforms to functional safety standards. And as part of that, the P8700 product that we're talking about here has been safety certified through a third-party partner of MIPS. And we did complete that certification earlier this year, reaching an ISO 26262 ASIL B level of certification.
And obviously functional safety has value in an industrial environment as well, yeah?
That's correct. Really, anytime a machine is operating near people or in an environment where it could cause harm, there are safety standards that typically come into play. So automotive follows the ISO 26262 standard. Industrial, depending on the environment, may follow the same, or it may be IEC 61508. Different industries have variations on the common functional safety standard. So we are, our certificate currently is for the ISO 26262 standard. We are building products and working to certify more broadly as well.
Okay. So in both cases, industrial and automotive, the functional safety is obviously important because, they're mission critical type applications where something goes wrong, potentially, someone could get hurt. So I guess that's, having those sort of assurances is really important, clearly. And having, again, the responsiveness to be able to act quickly and there not be any issues about, the reliability of the signal and so forth getting through, and the data being handled quickly. That's clearly paramount then, yeah?
Yes, so safety is largely about minimizing harm and basically avoiding causing any kind of harm. So anytime there is a fault detected or some deviation in proper operation, it's important for the equipment to reach a functionally safe state where it can either stop what it's doing or, in the case of a vehicle, stop safely, pull over to the side of the road, et cetera. So functional safety certification helps to build high confidence in the system that not only would the product be designed to operate correctly and perform its duties. But if there is a problem that is detected, then it can also safely wind down and avoid causing harm to people or to the larger subsystem that it's involved in.
Okay, that's great. And then obviously sort of coming more into the industrial side then, so as we said, there's similarities in terms of the responsiveness, in terms of the functional safety side of it. When you're talking about industrial applications and some of the projects you're working on with customers now, are there other particular characteristics that need to be taken into account?
Industrial has both its own unique set of requirements as well as analogies to the automotive space. So there are, in many industrial environments, the need to have multimodality sensing to sense the environment that a device is operating in. So robotics is the maybe easiest way to visualize that, where a car is effectively a robot that's operating in the street, whereas you may have AMRs or different autonomous robots that are around in a warehouse setting. You might also have some that are more fixed function, tethered to a factory environment, where they're connected through Ethernet and doing some kind of robotic arm articulation. So there are different robotic environments in a factory setting that also have the need for multimodality sensor input. You may also have fairly specialized industrial systems that are focused purely on sensing, where they, camera sensor, radar sensors that are monitoring production flow or some sort of assembly line, and they might feed through some sort of industrial Ethernet channel to a larger system for distributed processing. So there's many different types of form factors, many different types of equipments in an industrial setting that can leverage our products and do similar types of processing.
Okay. Moving ahead outside the factory floor, I guess, carrying on the robotics sort of subject, is we're going to get towards a stage where robots are going to be, sort of alongside human beings in a lot of different environments. So that could be actually in a production line in terms of a cobot working in tandem with human, so co-workers, but also it could be service robots in the home looking after people, elderly people with, helping them to remain independent and so forth. So I guess then that's again another challenging sort of area to deal with, because if you're going to be in close proximity to human beings all the time, you've got to make sure that their awareness of their environment and the AMI example would be, well, they're working around the factory floor, but they know to avoid things. But I guess if you're a service robot, you've actually got to be much more interactive with the human being you're dealing with. Is that a challenge potentially?
Yes. So autonomous humanoid robots operating in a home setting, you could think of that as maybe the pinnacle. Well, I'm sure we'll find a new pinnacle as we get to that point, but a pinnacle of physical AI, where you have something in a fairly unique environment doing a multitude of tasks, interacting directly with humans. So there's going to be a large amount of processing, directly at the robot for the robot brain that's going to be interpreting the surroundings, directly taking actions autonomously, and moving directly in close proximity with humans. So that brings in all of the pieces of the sense, think, act, communicate that we talked about, and is a highly integrated solution that brings all of these to bear. Leading up to that point, there will be a progression. We already have today somewhat fixed function robots that do a specific task in a more constrained environment. And I think what we're going to see is a progression of that building up to where you start to see multifunction robots that are in a less constrained environment, moving to untethered but closed system solutions that are in a kind of standard environment like a factory floor, and then moving out of the factory and into home and healthcare and other environments that are more free form. So it's going to be progression, and you'll see the processing requirements for both the kind of this brain function as well as even the fine grained motor control evolve to much higher levels as we get to these higher end systems.
Okay. In terms of your own devices, so you mentioned already the P8700 core. So that's RISC-V based. And well, first of all, what benefits has RISC-V, sort of adoption by MIPS brought to the company, would you say, first of all?
Yes, great question. So yes, the P8700 is actually the first CPU core that MIPS is producing that is the RISC-V native CPU. So MIPS has a long history and has developed many CPU products over multiple decades following the MIPS instruction set architecture. We have since transitioned fully to the RISC-V instruction set architecture. The P8700, as I mentioned, is the first product that is natively following that standard. Following the P8700, all of the MIPS CPU products are RISC-V based. One of the things that being RISC-V helps with is it is an open standard, meaning that anyone can build a RISC-V compliant CPU. And that brings several benefits to both to MIPS and to our customers. On the customer side, one thing that it brings is flexibility, and it avoids vendor lock-in. So we obviously bring what we feel is highly differentiated products to our customers that bring value for specific types of systems. If over time a customer does want to move to another vendor, or for whatever reason our roadmap offerings are not aligning to the customer roadmap, they can choose a different vendor that is building a RISC-V compliant architecture. So that brings in some flexibility on their side to have multiple potential IP partners, or even to develop a RISC-V compliant CPU internally in the future. For MIPS, there are other benefits as well with being part of RISC-V. One is we get to take advantage of the larger RISC-V community. So with RISC-V being an open standard and with multiple companies building RISC-V solutions, there are quite a few software tools, third-party partners that are bringing different solutions to the market and also contributing to things like compilers, operating systems, open source drivers, communication stacks, a variety of things that are not just for MIPS, but MIPS can take advantage of and bring to our customers to also bring into their solutions.
Okay, so that's in a nutshell. That's it's beneficial from the customer's point of view because they've got flexibility and they're not sort of locked into any specific vendor. But also from your point of view, you can sort of leverage the big sort of global ecosystem that's building up around RISC-V as well. So that makes sense. So in terms of the actual attributes that the P8700's got, in terms of some of the things we've said about dealing with multimodal inputs, having, to potentially deal with constrained environments and so forth, what are the sort of ways in which it's sort of ticking those boxes, would you say?
Yes, the P8700 is a very scalable solution. So the CPU itself is a capable CPU. It can run RTOS, it can run Linux and other a variety of different operating systems and higher level applications. The CPU itself, though, is not the full product or full solution. We are offering a cluster or even multi-cluster solutions to our customers. So you can have a variety of performance points that are solvable with the P8700 product. So each CPU can operate as a multi-threaded implementation, meaning you can have concurrent threads of execution that run at the same time through the execute pipeline of the machine. And we can, at the cluster level, instantiate more than one CPU. So our product offering does allow customers to scale from very simple single or dual core instantiations up to a many core system operating multiple threads in parallel for more complex systems. So again, if you go back to the sense use case and you have multiple sensors, multiple modalities coming in, as well as both background tasks and drivers and things for communication to other systems, it's important to have multiple concurrent threads of execution that might be spanning multiple cores, multiple threads within each core, and even multiple clusters in the overall compute subsystem. So the P8700 leverages all these features, and what that does is it allows a customer to put down less physical hardware to do these multiple concurrent tasks. So having that multi-thread, multi-core solution in a small area form factor, lower power footprint lets customers do more without spending a large amount of silicon area to do so.
which is great because obviously you don't want to sort of sort of have too much headroom in a particular design and then that not being used because that's going to drain power, it's going to take up space, it's going to have costs. But I guess also having the scalability is pretty useful because if you start off with a particular design, so say let's take a customer's doing an AMR and the initial one might be quite simplistic and it's only got a certain amount of functions it's got to deal with, but then the next generation model might have to sort of deal with different sensor data from multiple sources and have other sort of performance improvements that need to be addressed. So I guess from the customer's perspective, having it being able to work on one platform and then scale it up potentially to add more processing sort of horsepower into the system is quite useful then, yeah, would you say?
I would agree. Scalability gives customers the flexibility to have a common design across potentially multiple products that have different level of compute requirements. So one thing that can be done is to have two different configurations of the product, and maybe it's as simple as one product has a single cluster of multiple cores, and another product has two clusters. That gives an immediate scalability. But there are ways to also have varying numbers of CPUs per cluster or other variants in the system. But that does allow for customers to have common software. It's possible to write scalable software that can target different numbers of CPUs, and having the same type of solution across multiple platforms gives them the flexibility for a single code base that can target different form factors of their product.
Okay, so basically that just gives them that sort of versatility that they can sort of switch between different things without having to reinvent the wheel. Basically, they can, yeah. Okay, so that's quite cool. So that's really the product that's pushing a lot of your physical AI implementations. Then
that's correct. The PED 700 is targeted for physical AI applications. Sense is one aspect that we focused on pretty heavily here.
Sure.
Autonomous driving, self-driving types of subsystems is an area that MIPS has done over multiple years, and the PED 700 is the latest CPU product that we have that is targeting that space. It is a versatile product, so it's not a single function product. It is a RISC-V native CPU core. Customers can bring a multitude of applications to the PED 700 product. So it is well suited actually for a fairly wide range of application spaces. But that is, when we talk physical AI, the sense attribute is an area that we have focused on with this product.
So on top of things like factory automation and robotics and autonomous vehicles, where are the other sectors that are likely to benefit from physical AI in the coming years?
I think we're going to see physical AI permeate a lot of different application areas and environments. One area of expansion is going to be in the healthcare industry, and that actually has a variety of physical settings. You can obviously think of hospitals and doctors' offices where people go and become a patient and get serviced. The physical AI aspect in those environments could be things like assisting patients in and out of bed, assisting patients into a test environment, like for MRI scanning and the like. But it may also come to the home setting where you might be in a assisted living location with kind of higher end, more servicing equipment. But even in the personal home, whereas we get things like service robots or cobots, you could age in place and have assistants going to the bathroom, using shower facilities, eating, doing laundry, washing dishes, and the like. So we may see things that kind of blend between the home and the healthcare setting that will assist people as they age. And so I think there's going to be quite an expansion of physical AI and the types of systems that come into people's lives as these continue to evolve.
Especially because there's a shortage of workforce in a lot of those areas as well, isn't there? So that would be quite valuable. Yeah.
Yes. So it will be a way to help with the overall workforce and give people assistance that they need without a high demand on people-intensive resources. So it'll be a way to augment the physical labor required to help people as they age.
Yeah, great. And then elsewhere, where would you see other possibilities?
Another area where it could come into play would be in the aerospace and defense environment, where you have a lot of analogies to things in automotive. It's just instead of a car or a vehicle that's operating on a standard road, it could be drones, it could be equipment that's operating in a non-standard environment, so not a warehouse floor, not a highway, but off terrain vehicles exploring other planets or far reaches of Earth. There's a wide range of application spaces where intelligence at the edge and autonomy of a vehicle operating in non-standard environments is going to come into play.
Okay, so sort of that could be military sort of drones and so forth, and surveillance equipment and stuff like that. Okay, so that's cool. But it's clearly it is quite a expansive area for you guys to address, and I guess that's in itself brings quite a lot of challenges because you're going to have to be able to play in a lot of different markets. Is that going to be difficult for you?
That's right. There is a wide range of application spaces that we are targeting, and that's why we do center it around the sense, think, act, and communicate core principles. And the optimizations and areas of focus that we put into our products are centered on these four. And so as we look at, how do we build a system or allow our customers to build a system that solves physical AI challenges in a wide range of products, we center on how we do well at these four areas of operation, right? So again, the P8700 focused on sensing, multimodality, heterogeneous compute, and the ability to handle multiple concurrent tasks in parallel is one of the aspects that we bring that enable customers to build differentiated products that could suit a variety of markets, not just one.
That's great. Well, Dave, it's been a pleasure. Thank you so much for speaking to us. And I'll look forward to hearing more about MIPS's products in physical AI in the coming months. Okay, thank you very much.
Great. Thank you, Mike. Appreciate the conversation.